Hey everybody, this is Larry. This is day 13 of the January Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. Boats to save people. So I usually solve these live, so even the explanations are definitely, um, wait, fast forward toward the end if you're looking toward the solution or something. But okay. The I person has weight I. Each boat can carry a maximum weight of limit. The boat can contain two people at a time if the weight is less than limit. Return the minimum number of boats to carry every given person. That's interesting. So yeah, and each one can be. So the worst case is that given n people, we have n boats, and now we're trying to figure out how to match them up. Okay, so this is a little bit of trying to figure it out, and I'm just thinking about different ways of so the two things, right? One is I'm just trying to figure out ways to use greedy in some way, and then the other thing is just implementation, and how to prove them, right? How to prove greedy, which is always a hard part for greedy. I think the first thing I would do is sort them uh, by the what was it, by the weight. Okay, I don't know if that's sensitive these days, but then my other idea is that because the boat can carry at most two people. Anytime you could carry two people, it should be good if you um, minimize or maximize the other person, right? So basically, you want two people who add up to be as close to the limit as possible, and if you do that, and this is, and some of my explanation with respect to this is just playing around with a lot of numbers in the past, and this is just like an experience thing where I believe, um, like I don't know if I have a hard proof for this video, but basically the idea is that you know like like if two people have like very different weight and they add up to be near limit, you and this and one of them doesn't have a smaller fit, you would say that then it doesn't then you cannot get a better fit, meaning that okay, let's say if you have a limit of five. If 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 there's a person that's size one, um if it fits with four, then that means that like any heavier person cannot fit with it and so forth, right? So when I'm thinking about that, and I know that that's a kind of a terrible explanation, to be honest, but the way that I'm thinking about it is using that, we can do two pointers, right? We can just have a pointer to the smallest person or the lightest person and the heaviest person, and then kind of march toward the middle, to get the limit. And the reason why that we can do this is because, like I said, um, these examples are not very great for that actually. But let's say we have one, two, and this is also why we sort it, um, something like that, right? Well, five, that, and let's say limit is five to be clear. If we do the five, then five will be on the own boat. For four and the one, well, we know that it cannot fit, right? Um, and let's just add another. Let's just add another four for illustration. But yeah, we matched the four and the one. I think that should be obvious at this point. And then the second four, well, it doesn't fit with two, and because two is the smallest number that it can be, that it can match with, then you know that we have to get rid of four. So then we have three. Yeah, and then three and the two match, so then we put them in the same boat, and then now we have three. So I think that should be good enough for us to as a strategy, because I think we can greedy work. And like I said, some of the reason why I don't have a strict mathematical proof, because those things are always hard, especially live, because I'm not, like I don't have references and studies for it. But And some of that is where practice will come into play, where you deal with kind of the properties of these sweep line type number line type problems enough, then you'll kind of like almost be convinced about it. So then after that, it just becomes implementation. I think I think the and I could have said the same algorithm in different ways, and they have different implementation, even though they might do a similar same thing. But what I want to do is that I'll take the max, the heaviest person, see if it fits with the lightest. If it's if it is, if it doesn't, then the heaviest person gets its own boat. I think maybe that's a more intuitive way of doing it, or explaining it, because if the heaviest person and the lightest person doesn't match up, or like they don't fit on the same boat, then you know that there's no way that the heaviest person can um, can be with its can be with anyone else, right? Because everyone else is heavier. So then they get their own boat. And conversely, um, and if you kind of keep that invariant in place, that will always be true. So let's do it that way. And there are a couple of ways to do it. There are a couple of ways that we can think about implementing it. But the way that I want to do it, it's a little funky. Because um, because about you could use 2 pointers. I'll just use 2 pointers. So heaviest is equal to length of people minus 1. So this points at the last element, and then the lightest is equal to 0, and then just both is equal to 0 to begin with, and then now we have a while heaviest is greater than lightest. So if they're the same, what happens? Do we get them both? We might have to test that one a little bit to get the edge case of what happens if they're the same. I guess if they're the same, that's okay. But then we would have to add an if statement anyway, so that's why I'm not doing it that way. Because if you have to check an if statement inside whether heaviest is equal to lightest, then you might as well do it outside. So okay. So if the heaviest person plus the lightest person is less than or equal to limit, then we both increment by 1. Well, we always increment by 1 in either case, but if they're under the limit, then we can go we can move both the people. Do I have a typo here? I think otherwise we only moved the heaviest, so we can actually even take this out and do it this way, right? And then at the very end, if heaviest is equal to lightest, then we have to check that one case. Then we just do both is equal to 1, and then we return both. And this is not actually, this doesn't always have to be true, right? This actually is only true if there's only one person left at the end, because you can imagine, if you have 2, 3, limit is equal to 5, the heaviest actually points, the heaviest goes, starts at index 1, lightest starts at index 0, and then after one iteration, this actually goes to 0 and this goes to 1, right? So this is actually strictly less than. So yeah, okay. Let's actually run the case first before I celebrate. Okay, looks okay. So let's give it a submit. Um, Sometimes I get questions about running time, but in this case, I'm confident about looking. Like sometimes, I mention the constraints a lot, and in this case, because I kind of did it this way, I know that well the sorting is n log n obviously, and the rest is linear time, so I don't look at the constraint because you can't. It's very rare that you can do it better than linear time and sorting is pretty fast in general, unless you're doing something really funky, because libraries are pretty fast about it. But yeah, so what is the complexity of this? Like I said, this is n log n. This is O of n. And in terms of space, Depending on how you want to define it, we either have no, constant extra space, or because of the fact that we sort the people, and we really should not mutate the input. We should probably create another array of the same size and copy it over before sorting it. You could say that this is O of n space as well in a reasonable way, because now the person who passed their input here, it got mutated. But yeah, um, I think that's all I have. Hmm. I think you could also do like sliding window in the same similar way, or two pointers, by taking advantage of that. This is less than 30,000, but I don't know how helpful that is. So yeah, uh, for this one, because it is greedy, I'm gonna look at the solution and just go over it with y'all, just to kind of see if maybe there's another way, maybe if there's a flunkiness or something like that. But okay, yeah. So basically, this is the idea that I did. So yeah, except for their logic is the other way, where the lightest is with the heaviest. Okay, so I guess that's the only thing about it. Yeah. Oh, I like that they actually did the space complexity O of n, because I think because of what I said about the mutating input. So yeah, uh, cool. Let me bring this back up so that you could snapshot it or whatever. But yeah, that's all I have for this problem, I think. So let me know what you think. Hit the like button, hit the subscribe button, join my Discord. I would also say that these greedy problems, they take a lot of practice, because the actual proofs are hard. For me, I actually find greedy problems harder than dynamic program problems, because for dynamic program problems, you prove by being exhaustive, where for greedy problems, sometimes you have a hypothesis, and then it turns out to be wrong. Um, and the good thing about Leetcode is that you get the wrong, like they tell you what the case that you get wrong is, and you can analyze that. So that's why it's a good practice for greedy problems as well. But yeah, that's all I have for this problem. I will see y'all tomorrow. Bye bye.